Hello, I'm Andrew Purvis. I'm your Master of Ceremonies for today's webinar. I'm the General Manager for the Europe, Middle East and Africa region with the Global CCS Institute. I'd like to give you all a big welcome to today's webinar, which is presented by the EU CCS Network, the Global CCS Institute, in collaboration with the Road Project from the Netherlands. We have participants calling into today's webinar from all around the world, and you're all very welcome. Today's webinar is concerned with the reduction of fresh water usage at a coal-fired power plant with CCS by applying a high level of integration of all water streams. This is based on work that's been conducted by the Road Project. Let me start now by introducing you to our presenter, Mr. Andy Reid. Andy is a physicist by training, though his career has been as an engineer and project manager in the power industry. He's worked in combustion plant and boilers and subsequently moved to engineering and project management. He's also worked in an actual operating power plant in the performance department and project development also on new CCGT units. Andy is not new to CCS. He spent the last 9 years working on CCS projects, first at Killingholme and Kingsnorth in the UK when he was working for E.ON, and since 2010 he's been responsible for the capture elements of the Dutch Road project. In the current organisation that Road have in place, he's also got technical oversight for the transport and storage solution. Since working on CCS, he's learned a lot about the politics of the energy industry, about public perceptions, public relations, and stakeholder management. And it's excellent that we've got Andy presenting for us today. As we go through the webinar, attendees are welcome to submit their questions at any time. You can do this through the Questions tab on the GoToWebinar control panel, which should appear or should already be visible on your screen. These questions will be moderated and will be posed at the end of the presentation to Andy. Though you don't need to wait to the end of the presentation to submit your questions, you can do that at any time as they occur to you as we go through the presentation. We will try to get through as many questions as we can today, but please be aware we may not be able to answer all the questions today. So, without further ado, let me hand over to Andy Reid, who is our presenter.
Good morning. At least it's morning here, so good day wherever you are. First of all, I'd like to acknowledge my co-authors. Well, Hette Hilkemer is the second author on the screen. He's done most of the technical work, in fact, for the paper, so you should give him the credit for the technical details we've been able to include. And he's sitting next to me in case there are any difficult questions. And I've also got Mark Combrink, who's our communications, public relations lead, and he's also helped improve the slides so that they're easier to understand. They're both with me. The topic is the water usage. It's a fairly specialist topic, so I'm pleased that so many of you have dialed in. The GCCSI has put an insights briefing on the website that gives a sort of summary or background of this topic, looking at data for generic coal power stations. I'm going to be presenting specifically about the Road project and the design that we have here. First, a few words on the Road project, although I think most of you will be familiar with it. It's based in the Netherlands. It's a joint venture between E.ON Benelux and GDF Suez. I actually still work for E.ON, so I have two hats, one Road hat and one E.ON hat. And most of the people on the project are seconded in from one or other of the parent companies. We also have as intended partners TACA for the CO2 storage. They operate the platform, offshore platform for the CO2 storage site, and GDF Suez E&P, which is the offshore oil and gas bit of GDF Suez to do the transport. And we are very grateful for the funding we receive. European Commission, Dutch government, and the Global CCS Institute. As Andy mentioned, we are a member of the CCS network in the EU, which is a knowledge-sharing network involving all the projects funded by the European Energy Programme for Recovery, and it's also got one or two others. Statoil has joined with their Sleipner project. So that's a strong European collaboration on knowledge sharing. So that's who we are. A quick overview of the project. This diagram is not to scale, but it's just to illustrate that it's a full chain, carbon capture, compression, offshore transport and storage. It's not full scale. It's only about a quarter of the power station that has the flue gas diverted to the capture plant. But it does have full chain, and it does have full heat integration. Located on the E.ON power station here. Just to make a point, this is all the harbour of Rotterdam. This is now also harbour, but it means we've got very good access to seawater for cooling. We're very close to the North Sea. This thing here that you can see on the map, just out of interest, is a big materials handling, coal handling facility. And if you see coal prices quoted as the Rotterdam benchmark, that's the location of the input facility that sets the coal benchmark. We have very good access to coal from all over the world. This is the E.ON plant as it looks pretty much now. It's still formally in commissioning. We've had a few technical problems. It should have been fully operational by now, but it's nearly there. We're in hot commissioning, and it looks completely finished. So we've got the turbine hall, the boiler house, the electrostatic precipitators, the FGD column here, and then the stack. There's no cooling towers because it's direct cooled, and the cooling water comes from the right-hand side on this plot, through the power plant into this discharge pond, and then out to the harbour on the left-hand side. This is more of an aerial view, and you see the area in red, picking out where the capture plant is going to be located. So the power station's a big one. It's 1,070 megawatts roughly, net output, a little bit above 46% efficient, based on lower heating value, and that's partly because it has very advanced steam conditions, 600 degrees C, 620 steam conditions, and partly because of the direct cooling and low seawater temperatures. The average seawater temperature is about 12 degrees. The capture plant is sized at 250 megawatts, and that's before taking the power reduction from the capture plant into account. So it's just under a quarter of the power plant flue gas, and it's that size because that's what the grants from the EU would pay for. 90% capture efficiency. If you do the sums and assume it runs 365 days a year, full load, you get about 1.5 million tonnes a year. The coal plant runs according to the market and therefore isn't on all the time, and the capture plant is a single unit demonstration. So the 1.1 million tonnes headline takes account of the fact that it won't be running all the time. That's not a base load figure. The base load figure is 1.5. I think, what else do I need to say about that? I should say something about the stack and the cooling system. There's no gas heater in this plant. It has a wet stack, so the flue gas coming in from the boiler gets quenched in the FGD and then comes up here at about 50 degrees and goes into the stack. And our flue gas tie-ins for the capture plant will be in the stack. So in terms of the water balance, the important thing to be aware of is that the flue gas is saturated at about 50 degrees as it goes into the stack. and that's a significant water loss. And the FGD takes about 120 tonnes an hour of water to quench the flue gas, which is, it's not drinking, it's sourced from a nearby freshwater lake. Transport, just very briefly, we have a pipeline to the offshore storage site, 26 kilometres. The most expensive bit is that there are two directional drills, one to get under the mouth of this harbour, and the second one, the big one, to go under the shipping lane. That's the main shipping lane into the port of Rotterdam, which is Europe's biggest port. So they didn't want us to dredge it and close the shipping lane for some reason, so we'll have to do a directional drill. And the offshore platform, you can actually see the power plants and the Maasvlakte in the background, that it's that close to shore. This is a normally unmanned platform. We will reuse one of the existing wells, and that makes it all a relatively cheap project. A short transport pipeline, reuse of existing offshore infrastructure. But I won't go into any more details of that because it's not the focus of the talk. The other thing on the introduction to road is just to say what the current status of the project is, which is stalled at the moment. We've done all the detailed engineering. We have a complete capture plant. We've done a lot of the detailed engineering, and in fact we've got some of the long lead components still contracted, well, I should say already contracted and suspended. The pipeline route's engineered in a lot of detail. The flue gas tie-ins are actually constructed, so there are T-pieces inside the stack to take the flue gas out. There's a lot of work done, and basically the whole thing is complete apart from the decision to actually build. Likewise, the permitting is all sorted out. We have a capture permit, we have a storage permit. The transport permit is agreed, but is on hold until the project is definitely going ahead, because the pipeline route onshore will sterilise a strip of land for future pipelines, and the authorities have said that they will give us the permit as soon as they know we're going ahead. So it's all agreed, it's not a problem, but you can't find the definitive irrevocable storage permit published. We also have contracts agreed with all the relevant parties for E.ON, for the power plant, for GDF Suez, for the transport, for TACA, for the storage. They're not signed because we don't know when we're going to start, but they are all textually agreed. But because they're not signed, we have lost price validity on the main contracts. The problem is finance, as with most CCS projects. We thought we had sufficient finance when we started all the detailed work, but when we started in 2009, 2010, the carbon price was 20-25 euros a tonne and rising. And we were expecting the carbon price to be 30 plus and paying for the operational costs of the power plant. The carbon price is much, much lower than that, and that's created a big hole in the funding. And we've been negotiating for several years now to try and solve that problem. We have made some clear progress. There has been some recent commitments of some extra money. The one in the public domain is Norway. We also have some other ideas, so I think 2015 might be a good year. It might see us finally cross the line and get started. But as things stand, the engineering and the technical work is all on hold. So that's the background and where we are with the project. Now I'll turn to the technical details for the topic. And this is probably the most complicated slide I will show, although there are one or two others as well that are a bit awkward. But I'll run through this. This is a very standard slide for a carbon capture plant. It's in fact a generic slide. It doesn't have some of the specific features of the Flue design. It doesn't have a lean vapor compressor. It doesn't have intercooling. But it's here just to illustrate the water flows so that we can talk about the water usage. And I'll just talk you through it and explain the water flows going in and the water flows coming out. And I'll do it piece by piece. So the first piece is the direct contact cooler. The capture plant operates at 30 to 35 degrees, around that temperature. The flue gas comes in from the power plant at 50 degrees, saturated, as I've said, saturated from the FGD. So the first thing that happens is that it's cooled. This takes cooling water, but it also generates a lot of water. As the flue gas is cooled, the water condenses out of the flue gas. And this stream, excess DCC water, the wastewater, is really quite significant. In fact, the DCC cools the flue gas to the point where there's actually less water in it than there was when it went into the FGD. Then we have the deep FGD, and that's a much more minor component. So it's basically a simple closed loop. There's sodium hydroxide added and sodium sulfite and sulfate coming out in the waste stream, but they are very small streams. They're less than 1 ton an hour. Well, all the small streams combined are less than 1 ton an hour. The next big one is the absorber, and again this requires, because the reaction with the CO2 and the solvent is exothermic, this requires cooling, so there's a cooling water demand. At the top of the absorber you have a wash section which is to remove the amine. In order to keep the amine concentration low in that section, that has a continuous supply of beam-in water going into it, which then flows down into the main column. So this means that this is always receiving fresh water. So in order to keep the water balance in this system, so you don't steadily dilute the solvent, the flue gas actually leaves here a little bit hotter than it came in. So there's some evaporation as well. And that means that the DCC cools to cooler than the flue gas leaving the plant. And that's how the wash section is kept dilute and the water balance is maintained in the system. The next part is the stripper column. The main thing here is that it takes a lot of steam from the power plant to heat up the solvent and regenerate the CO2. In terms of the water balance, this doesn't have any effect because it's all neutral. The amount of steam coming from the power plant is matched by the condensate going back. But it does mean that there's a lot of steam condensed from the power plant, and that means that the power plant main condenser requires less cooling water. Effectively, you've transferred some cooling duty from the power plant to the capture plant. Then we've got what Fleur call the overhead stripper condenser, or the stripper overhead condenser. So the CO2 comes out of the top of the stripper at around 100 degrees, and it needs to be cooled before going into the compressor, and cooling it also condenses a lot of the steam out that's come away with the stripper. And this is an area where we've managed to do some direct heat integration with the power plant. So this component is actually cooled by power plant condensate, so it provides feed heating duty to the power station. And the condensate is returned into the feed train, just as the condensate from the stripper is returned into the feed train at an appropriate temperature. So that's another part of our heat integration. The final component to understand briefly is the compressor. We did look at doing heat integration with the compressor and using power plant feed water to cool the compressor, but that has a significant disadvantage because it's warmer, and therefore you have to compress the CO2 when it's hotter. And we found with our system, because we've got very cold cooling water from the sea, the penalty in terms of compressor power that we take if we use condensate is too high. We're better off just using direct seawater cooling. So those are the main streams. Also worth just mentioning briefly, there is some waste from the reclaimer. There's some water in the CO2, but we dry the CO2 to 50 ppm. The CO2 and the reclaimer and the wastewater from the deep FGD combined are less than 1 tonne an hour. So it's so those are very small. So those are all the water streams. This slide shows a recap of our chosen explains our chosen cooling system and mentions the condensate that's used to cool the overhead stripper condenser. So the cooling water supply for the power station we take after the main inlets for the power plant, and that's because the main cooling water intake had enough margin for us, and it's quite expensive and a difficult permitting challenge to get a new cooling water intake. So we use the existing intake, but we take the cooling water round MPP3 to the discharge pond. It would be cheaper to put it back in before MPP3. That would give us much shorter ducts because of the plant layout. But then we'd be putting warmer cooling water into MPP3 into the power plant and reduce its efficiency. So that's the basic layout for the cooling water. So now I'll give you the numbers. First of all, the power station. So it requires a fair bit of deeming water. It's a once-through supercritical plant, so it runs on very high purity water. It's slightly unusual in that it doesn't have a main water treatment plant on site. Rotterdam's very industrial and there's lots of plants in the area. And in fact, the deeming water is bought in over the fence. That turned out to be cheaper. And then there's a polishing unit that brings it up to the quality required for a supercritical plant. So the deeming water actually comes over the fence. We've got water coming in effectively in the coal. Some of it's moisture in the coal, some of it is water that's formed during combustion because there's hydrogen in the coal, and when you burn it, that forms water, forms steam. So in terms of the water balance, that's quite an important feature, that there's 155 tonnes an hour coming in from the fuel and the combustion process. A small amount of rainwater. The fresh water I've mentioned, this is used in the FGD to quench the flue gas. Brings the flue gas down from above 100 degrees down to 50. And there's a small amount of drinking water. And then the main water usage, which is the seawater cooling, and this is direct cooled. So then the water coming out, the seawater, now we've increased the seawater supply coming out, and that's because a lot of the waste streams are treated to a quality where they can be discharged into the sea. So some of the deeming water and other water sources end up in the seawater. The flue gas, you can see a big increase in the water in the flue gas from the water in combustion, and that's because of the quenching effect of the FGD. Adding water, and there's a few other minor losses. This is either water that escapes as steam or wastes that are not of a quality that they can go into the seawater. So that's the main power plant, and that's the reference point. Now we can talk through the impact in terms of the water balance of adding the capture plant. Those are the charts you've seen before, but some of them have changed. The ones with the red circles have changed now. The freshwater consumption has fallen, and that's because we've added direct contact cooling water into the FGD. So this was 120, it's fallen by 44 tonnes an hour because the condensate that we're condensing in the DCC is replacing that fresh water. We also see a reduction in the seawater usage because we've diverted steam away to the capture plant, and so we've reduced the cooling demand of the main power station. For the capture plant is reducing the water in the flue gas because of the quench in the DCC. It comes back at between 30 and 35 degrees or thereabouts from the capture plant, and it's had a lot of the moisture removed. So the water in the flue gas has also dropped coming out of the whole process. The capture plant has some deem-in water usage, as I've talked about, so that goes in at the water wash section of the absorber. It has the steam and water for the reboiler and the condensate that does the heat integration and the overhead stripper condenser, and it has its own cooling water supply. And you can, well, yeah, if I go on to the next slide, this has got the boundaries on the totals for comparison in numbers, and you can see that the overall cooling water demand has increased. Although the cooling water demand for the power station has dropped, the overall number has increased. It's gone up by about 6%, and on a per megawatt basis that's about 12% because the capture plant has reduced the output overall by about 55 megawatts. Maybe 60 megawatts, depends on the load. And that's a combination of the effect of the steam offtake and the works power of the capture plant itself. You can see that the freshwater consumption has fallen because we've recycled the condensate collected from the direct contact cooler, which is the condensate extracted from the flue gas. The deem-in water consumption has gone up. It's unusual for a power plant to have separate freshwater and deem-in water supplies. It's more usual for them to do their own water treatment and have a single water supply. So I've put a line here which is simply a combination of those two to show what's more typical of a power plant, and what you see is a 23% reduction in the freshwater supply, which is very close to the percentage of carbon capture we have on the power plant. That's the situation as we have it, and this has all been very carefully designed and calculated, and these numbers are all exact. To make it more, the information more transferable, we've also done a calculation of what happens if you go to full-scale capture. Now, at this point, what we've done is scaling of the design from the road case, with some practical assumptions built on top of that. So these numbers are reasonable, but they're not precisely engineered for any real particular case. First of all, we have the power plant water usage, and this basically looks the same as before, except that we have been able to eliminate all the freshwater usage completely because we can get it all from the direct contact cooler. We have a further reduction in seawater usage and in the water in the flue gas coming out. And in fact, you can now see that the water in combustion going in is more than the water in the flue gas coming out. So the capture plant is actually extracting water that was in the carbon. We have introduced a deem-in plant, deem-in water treatment plant. That's a more generic case, but also we had too much fresh water in the DCC for the FGD, so we have to use it for making deem-in. So we've introduced a deem-in water treatment plant, and the deem-in supply to the power plant is unchanged from the previous layout. This slightly complicated layout explains the deem-in water supply. So we have the deem-in water for the power plant, we have deem-in water for the capture plant, so 76 tonnes an hour required. The direct contact cooler now produces 188 tonnes of water, and 120 tonnes an hour is used in the FGD. And that leaves 68 tonnes free to go into the water treatment plant, which pretty much balances the amount of demin you need. The problem is that you don't get a perfect water treatment plant. Water treatment plants always have some wastewater, which contains all the things that you've removed from the pure water. We haven't done a detailed calculation on that. We simply took the wastewater stream as being about 10% of the incoming fresh water, and that means that we do need still need some fresh water for the water treatment plant, but it's not very much. And if I'm honest, the power plant is not designed with a high focus on minimising water consumption. There's plenty of water in the Netherlands, and it's a coastal site. So I think if you were building a power plant in an area that was constrained on water, you could almost certainly reduce this fresh water to zero and have the plant self-sufficient in fresh water, apart from cooling. The remaining streams, I think we've covered enough of this that you can probably understand it. So the flue gas has a lot of water removed from it now. The reboiler steam and condensate is still in balance. And we've now got 52,000 tonnes an hour of cooling water going through the capture plant. So there's almost as much cooling water going through the capture plant as going through the power plant in this layout. And to finish, we have the table that puts all the ins and outs in straight numbers. So we see the cooling water for seawater demand for cooling has gone up by 25%. That would actually take us above what our existing cooling water intakes can take at MPP3. So if we were to do this, we would need a new cooling water intake. Or we'd have to put a cooling tower on or something like that. You can see that the increase in cooling water demand dwarfs the freshwater usage and freshwater consumption. And on a per megawatt basis, 63%, this is a big number. It's partly due to the loss of efficiency in the process, but it's also due to the fact that we're cooling the flue gas down to a lower temperature. So we reduce the heat that's emitted to the atmosphere in the flue gas and put it in the cooling water instead. I did try and do some calculations thinking, well, if you had tower cooling and you were evaporating water, how much water would you evaporate? And whether, if you think in terms of the water evaporated, would it still swamp the freshwater usage? It's about 4 times bigger on my simple calculation, so it's still the dominant effect. I wouldn't say it quite swamps it, but the cooling water demand is dominant, even if you're only considering the evaporation from a tower system. For freshwater usage, you can see that we have almost eliminated this entirely. So the only freshwater usage is our nominal amount to cover the wastewater that's coming out from the demin plant. So in this configuration, we've almost got a water neutral power station apart from the cooling, and because we've got direct seawater cooling, that's not a big problem. So that's the end of the sort of main technical part of the presentation. The conclusions just give a recap. So for the basic road plant, which is just under a quarter of the power plant, we get a 6% increase in cooling water usage and a 23% reduction in freshwater usage. And at full load, if we were doing 100% CCS, we would have this 25% increase on a site basis and 63% on a per megawatt hour basis, which is a big increase in cooling water. But the other water usage falls to almost nothing. That's the presentation. I hope it's all clear, but please use the questions to ask if anything's not clear. And at that point, I'll hand back to Andy for the question session.
Thank you, Andy, for your presentation. So we now have an opportunity for any of our audience to submit questions, which we can put to Andy and his team. As I mentioned, you can do that using the pop-up box, which is visible as you're watching the webinar. A number of questions have come through already as we've gone through the presentation, so I'd like to start with perhaps a couple of those. Andy, literature sources report an increase of cooling water use of around 76% on a megawatt hour basis for a post-combustion capture plant at a supercritical PC plant. Could you give an indication of what you think the water increase would be without the waste heat integration at road, i.e. what's the impact of the technology, the engineering you've been talking about?
I think it's actually relatively small, less than 1% in terms of the impact of the stripper condenser. I think there are two other factors that makes our figure lower than the normal literature. One is that it's a very efficient plant with a low flue gas temperature coming out of the plant in the first place. I think that's lower than average, and that's partly because it's new and highly optimized for efficiency, and partly because of the fuel specification. You know, if you're burning a lignite or a high sulfur coal, you simply can't go to such low temperatures. The other thing that makes it efficient is that we are very lucky with the IP-LP steam crossover pressure. So we take the steam off the power plant at almost exactly the pressure that the capture plant wants it. So the efficiency reduction as a result of the capture plant is pretty good. So I think if you didn't have the specific heat integration with the stripper condenser, it would only save maybe 1% of the cooling water flow. Although it would change it, because you would have much more cooling water going to the capture plant, but the main power station would be using the steam to heat the feed water. So you would redirect cooling water from the power station to the capture plant.
Okay, thank you. With regard to the cooling seawater intake, has this been designed with additional capacity in terms of future expansion for the capture, for further capture units retrofitted to the plant, and have you factored that into your associated permits for seawater intake?
No, the simple answer is no on all counts. The power plant was permitted without carbon capture, although it is carbon capture ready. And if we do full-scale carbon capture, we will have to have a new cooling water intake. Okay. We are actually very close to the limit. At certain summer conditions, we will struggle for cooling water with the capture plant running with the design as it is. It's fine for most of the time, but we're basically using the margin that was in the original design.
Okay.
And that lets us get away with 250 megawatts of capture, but we wouldn't get away with much more.
We've been asked, could you give an indication of the efficiency gain associated with heat integration in two cases? One is of the overall of the overhead CO2 condenser, and secondary of the overhead CO2 condenser and the CO2 compressor. As a follow-up, did you also consider full integration of all the capture plant's condensers?
Right. The heat integration with the overhead stripper condenser is about 0.2% in percentage points. The benefit of that. We didn't see. I don't have a number for the CO2 compressor, it was very marginal because the problem is if you use the condensate to cool the CO2 compressor, you don't get as deep cooling, and then the CO2 compressor has to run with hotter CO2, so you get an increased power consumption from the compressor. And what we found was that the benefit was very marginal in our case. So it's not effective to use the heat integration using the heat from the CO2 compressor. I think there's a cost element there. If you combined using condensate and using cooling water, you could achieve an efficiency benefit, but that would be at a higher cost, and we didn't consider that. In terms of full integration of the other capture plants' condensers, well, we have covered all the condensers. There's not a lot more we can do. So we did look at all the coolers. The problem is that the capture plant runs fairly cold. It runs at 30-35 degrees, and so the cooling parts of the capture plant are simply too cool to allow effective heat integration. What we've got here is actually not far off as good as you can get.
Okay, thank you. Andy, based on your experiences of going through the design process on road, would you have any recommendations for the capture readiness of a power plant in regards to water systems as people look to design and construct capture-ready power plants?
Well, I think it's worth being aware of the increase in water consumption and making sure that additional cooling is available for the full carbon capture. Capture readiness is a difficult one because the cooling water load and well, all the tie-in points tend to depend on the specifics of the capture technology selected, and therefore it's difficult to do a design that's optimised for a future technology if you don't know exactly what the future technology is. My perspective on capture readiness is simply to make sure that you have the gross systems available. So you have enough space, you have enough cooling water, you have somewhere to put the CO2 and a CO2 pipeline or transport route that's credible. And as long as you've got those things, the likelihood is that you will be able to fit CCS. I've been involved in a fair number of CCS projects and a fair amount of research, and in the studies that I've seen, we've never actually found a power station that can't be retrofitted with capture. So I think capture readiness is a fairly loose concept, but certainly you need to make sure you've got access to the cooling water and fresh water requirement.
All right, thank you. Do you see any corrosion issues because you're using direct seawater cooling? And what materials have you used to construct the heat exchangers that are exposed to that seawater? The
heat I think they're all titanium, is that right? Yeah, I'm getting a nod from Heather. They're all titanium heat exchangers. It's the same basic design as the heat exchangers in the main power plant condenser. So we don't expect corrosion problems. We have looked quite carefully at the layouts, particularly where you've got cooling of the solvent. And the issue there is that the solvent is at higher pressure than the cooling water. So you shouldn't get solvent contamination from the seawater. and the solvent is you will pick up the leak fairly quickly. So we don't see a big risk. We don't see a big environmental risk, but we are using high quality materials.
Sure.
Right. Okay. The pipelines, the cooling water pipelines are GRP, glass reinforced plastic.
Okay. Thank you. Have you looked at part load operation with capture, and is it possible you could say something about how water balances and perhaps efficiencies will change under part load?
Oh, I haven't thought about that one. We certainly looked a lot at part load, and one of the things we've looked at very hard for our project, which is unusual, is running the capture plants flat out while the power station's at part load. And that's because when the power station's at part load, the electricity price is low, and therefore the efficiency penalty is cheaper. So that's the time when it's most cost effective to do your carbon capture. And of course, the power station, the capture plant is only 25%. Takes only 25% of the flue gas, so the capture plant can continue to run at full load even when the capture plant's at low load. Well, the water loss would obviously increase in percentage terms because the percentage of capture is increasing in that scenario.
Okay. All right. Thank you. Does the CO2 product that's generated by the capture plant with this approach have a different water content than would otherwise be the case? And if that's the case, has that impacted your engineering plans with regard to transport and storage?
Right. The CO2 is actually specifically dried after it's cooled with the overhead condenser. It goes through the compressor, and the first stages of the compressor are wet, and as each intercooler within the compressor, water is condensed out and collected. And halfway through that, well, at about 20 bar, which is after the low pressure stages of the compressor, there's a dehydration unit, which is a mole sieve, and that is specified in order to achieve the dryness that the transport system needs, which is 50 ppm of water, and that's a fairly conservative figure. It's based partly on the transport system. It's also based partly on concern over hydrate formation in the well, if you get low temperatures in the well. So the water content is set by the transport system, and the transport system runs with conventional carbon steel.
Okay. Thank you. We have one, I think, final question, more a clarification question, Andy. Did you say the flue gas enters the stack at 50 degrees? And what's the final flue gas temperature?
Right, the flue gas from the FGD enters the stack at about 50 degrees, so that's the current plant design. The road plant, the capture plant, would cool it down to about 35, and so and that would then mix. So you would have 50 degrees C flue gas from the FGD. At 75% of the flue gas would be that, and then 25% would be at 35 degrees C coming from the capture plant, and they would mix. Off the top of my head, I don't know exactly what temperature that would give. That does actually give some extra mist formation. The mixed flue gas will be slightly oversaturated, and so we'll get slightly more condensation. So it'll be a slightly wetter stack than it was before. But it'll and slightly less buoyant because it's cooler. But that has all been modelled and permitted.
Okay, thank you, Andy. That's probably a good time to draw things to a conclusion. Unfortunately, we didn't get time to go through all of the questions that we got in the allowed time. We'll do our best to get back to those who've asked questions subsequently. But if you still have questions that you would like answers to, you can still submit them to the Institute through the webinar inbox. Which is webinar at globalccsinstitute.com. Webinar at globalccsinstitute.com. This webinar has been recorded and it's going to be made available on our website. That will happen along with a copy of the presentation, so with a copy of the slides in the coming days. So finally, I'll just like to thank our presenters again, and as you are leaving the session today, we've put together a very quick 3-question survey. We would really appreciate you taking the time to complete it to help us improve our webinar program. This webinar is one of a series of webinars that the Institute will continue to run throughout the year, and we look forward to your participation in future online events. I certainly hope you found this webinar valuable, and once again I would like to thank you all for your attendance and wish you a good day.